So we have this very well-defined mathematical task ahead of us. We are going to take this total energy and take its derivative of these terms, manipulate it somehow, and then try to massage it until we get a form that looks like minus this term. When we do that, as you can see, we're going to be dealing with derivatives of our various electric and magnetic fields. And for that, we're going to need to know some relationships among our fields. And of course, those relationships are Maxwell's equations that govern the behavior of our fields. Now, because we will be dealing with derivatives, of course, the most convenient form for this type of field theoretic investigation is Maxwell's equations in their differential form. So let's just review those very briefly. I have those for us here. I'll spare you the time of my writing them down, but just for you to recall, remember the divergence of the electric field gives us the charge density at any point divided by epsilon naught. That's a very quick way. That's Gauss's law in differential form. It's a quick way to check your electric field is right because its divergence gives you the charge density. The second equation is the direct analog of this, but because there are no magnetic charges, the magnetic charge density is always effectively zero. Then down below here I have Ampere's law, which recall does actually include the displacement current term when you want to be exact about things. And we want to be exact here because we don't want any way energy can sneakily leak away on us. We want the exact equation as far as we understand it. And then finally over here we have the most recent equation we thought about, Faraday's law, which is very parallel actually to Ampere's law. It has the time derivative of the opposite field, and with certain prefactors, and this minus sign of course represents Lenz's law for us. There are no magnetic charges, and so there are no magnetic currents. There's a current term here for electrical charges for the magnetic field, but that corresponding term is missing in Faraday's law because there are no currents of magnetic charges to affect the electric field. So these are the equations that we have to work with, and our main task now is to begin the task of taking the derivative of this total energy. So I'm going to begin then by beginning to calculate that derivative. So note now that when I take the time derivative of the total energy stored in my volume, that of course the time derivative being, here is a total derivative, but this total energy doesn't depend on locations in space, right? It's just a function of time t. So I could either take the total derivative or the partial derivative of that total energy. It doesn't really make that much of a difference. Now, here comes the one of the key mathematical steps. When I look at my formula for the total energy, what it is it's an integral over different locations in space. And I want the time derivative of this. But as we know, an integral over space is really just a sum over spatial locations. And I want the time derivative then of some complicated sum. But the derivative of a sum equals the sum of the derivatives. In other words, I can write the summation first, namely the integral, and have a sum of derivatives, or an integral of the time derivatives. All this says is that the time derivative I'm taking can be moved inside the integration. So then this would become then an integral over all of my volume of the time derivative of what's inside my integral here. So now I have to take the time derivative of these two different terms. So I'm going to need, of course, the time derivative of this term. I can pull out the constant prefactor, epsilon naught over 2, but I'm going to then need the time derivative of the electric field squared, and I'm going to write that down. And similarly, I'm going to need the time derivative of the magnetic field quantity squared times these prefactors. So let's work on time derivatives of our electric fields, for instance. So we know we're going to have, of course, epsilon naught over 2. And what I really need to calculate at this point, a little sidebar that we're going to have is, what is the time derivative of the magnitude of the electric field vector squared? No, first time derivative of the quantity of E squared. Well, if you remember what E squared actually is, that is where you take the x component of E and you square it, and then the y component of E, and you square it, and the z component of the electric field, and then you square it. Many times doing these vector identities is as simple as simply writing out the components and then doing your normal type operation. So when I take these derivatives, I think we can see we're going to get a sum of three different terms, right? The first term, when I take this time derivative, is I have the square, so I bring down a factor of 2. I then have the x component of the electric field times its derivative, which is partial of the x component with respect to time t. That's the first term. Plus the second term, the time derivative of this, is twice the y component of the electric field times its derivative by the chain rule, dEy dt. And then, of course, there's going to be the third term, which is the same, 2ez times partial that z component with respect to time t. Now, once we've worked out things in components, it helps us to get things back into their compact vector notation. And I think you can see what's happening here. Overall, there's a factor of 2 that has come down. And what's left is the x component of E times the x component of the time derivative of E. And then the y component of E times the y component of the time derivative of E, and so forth. So this really looks like a dot product. And it's the dot product between the electric field and then its time derivative. Because the electric field gives me my components Ex, Ey, Ez, and the time derivative of the electric field gives me my components partial Ex dt, partial Ey dt, partial Ez dt. And then I just have to add those three together, and so I have this result here. We also, as we have this result here, right, which then represents the time derivative of E squared, so I can put my term in right now. So that's 2E dot partial E partial t, remembering that this had to be the time derivative of the magnitude of the electric field squared. And of course, for the next term, I'm going to need, as we can see, 1 over 2 mu naught times the time derivative of b squared. So I will need 1 over 2 mu naught. And when I take the time derivative of the magnitude of b squared, you can see, of course, I'm not going to drag you through it, that you just write out exactly the same thing, except there'll be b's everywhere where there were e's. So this will be just twice the magnetic field dotted with its time derivative. And that then ends our little aside here on taking derivatives of squares of fields. And then the factor here is 2 times the magnetic field times its time derivative. And this whole quantity, of course, is integrated with respect to volume V. So what we've done then is we've just taken our integral for the total energy and moved the time derivative inside and taken that time derivative. Now, from this, I think we can begin to simplify and reduce things a little bit. Our factors of 2 here cancel nicely, as do our factors of 2 here. So let's rewrite this a bit so we can continue manipulating our equations to see what our field theory is going to tell us. So the time derivative of the total energy that we are hoping will give us minus our power coming back out is now an integral over the whole volume V of a sum of 2 different terms, and we hope now to be able to manipulate these terms a little bit. And the terms involve, as you can see here, epsilon naught times E times its time derivative. So there's epsilon naught, the electric field times the time derivative of the electric field. And then the next term had 1 over mu naught. And then the same structure, the magnetic field times the time derivative of the magnetic field. Now this is all nice, but it doesn't quite look yet like the power density that we were talking about. Remember, the dissipated power is something like electric field dotted with current density. And I don't really see that kind of a structure in here yet. We need some way to manipulate this. We need some extra relationships that we can use to make some progress on this mathematically. And of course, those relationships are the Maxwell relationships that we are looking for. So let's see what we know about, for instance, the time derivative of the electric field. We can find that in Maxwell's equations. One of these terms has it. Here is the time derivative of the electric field. So I can substitute in for this, right? To solve for dE dt, for this fourth Maxwell equation, what I would do is I would subtract mu naught J from the curl of B, and then just divide by mu naught epsilon naught, and that would give me the time derivative of the electric field. So that's what we're going to be substituting in for this first term. So let me just talk about our integrand here. So the first term, as we just said, becomes epsilon naught times the electric field dotted with the time derivative of E. And we just showed you that that would have to be then the curl of the magnetic field minus mu naught J, all divided by mu naught epsilon naught. And that replacement is coming to us from, of course, this fourth Maxwell's equation. I can call it M4. And we're going to now look at the magnetic field term. But before we do that, I just wanted to notice we have a nice cancellation occurring here. I've got epsilon naught in the numerator and in the denominator, so those epsilon naughts will cancel out nicely for us. Now, how about the next term? The next term has 1 over mu naught times the magnetic field dotted with, now I need the time derivative of the magnetic field. And that we can see here, right? That comes from Faraday's law, Maxwell's third equation. That is just minus the curl of the electric field. So I'll have an additional term here, which is going to be minus the curl of the electric field. And this, of course, is coming from Maxwell's third equation, or Faraday's law. Now, let's see what we have here. Oh, very nice. Notice something here. I'm very excited here because look, I've got E dot and then I've got J. It looks like E dot J. Remember, that was this power density term. I am getting the power density out of this thing. So let's pull that term out and see what else we have left over. So let's continue this simplification. So let's just focus on this mu naught J term for now and see what it gives us. So what we're left with is, you can see here, there's a minus sign, which I really like because we want minus the power coming out. So let me factor this minus. I'm just going to write down the J term, but first I'm going to factor out this minus sign. So there's going to be minus. So I've accounted then for that minus sign. I have my integral, of course, over the volume where all of these experiments are going on. Then what I'm left with in here is, wow, look, a lot goes away for us. So I have the electric field, that's good, dotted, I already did this, minus sign, mu J over mu. Oh, perfect. The mu's will cancel out, and I've done the minus sign, so that's all that's left is the J, dotted with the electric field, integrated over volume. And that then accounts for this mu naught and this J and this E out here. So I've now accounted for that entire term. And that, I'm going to put a circle around it because we're done with that term. And that is so perfect because minus the integral of J dot E over the entire volume, integral over the whole volume of J dot E is the power that comes out, the work that these electromagnetic fields are doing on the various particles inside of my box. So that is really very nice. That's perfect. PQ out. Now, unfortunately, it looks like we have some additional pieces, though, right? There are these two other terms, E dot curl B and B dot curl E. They haven't exactly perfectly canceled out on us. So unfortunately, it looks like there is some additional power term. Well, you know, fortunate or unfortunate, I mean, we've just learned something about electromagnetic theory. There's some interesting other way it looks like power can get out of our system. So let's try to figure out how that form should work also. In terms of the accounting of conservation of energy, the power coming out in this other way should appear with a minus sign. So I'll pull out a minus sign. So what I write down next is the other way power can get out of our region where we're doing these experiments. And I still have it as some integral over the entire volume. And if I'm going to pull out this minus sign, I guess I will write this term here first. So I've got B dot curl E over mu naught. And when I look at the other term, it's in here with a plus sign, but because I'm factoring out a minus sign, I'm going to have to write it down with a minus. But it's E dot curl B, but notice it's also divided by mu. So I've got a common factor of 1 over mu naught. So let me write that down first. So there'll be a factor of 1 over mu naught times then two terms. I've pulled out this minus sign, so this term can show up as a plus. So I will have B dotted with the curl of the electric field. That then takes care of this entire term here. Then what's left is this term, which I will write with a minus sign. So this minus times this minus gives me the plus that I'm seeing here. There's the 1 over mu naught. So all that's I'm left with is E dot curl B. So there's E dot the curl of B. And then that completes the terms that are multiplying 1 over mu. And then that can be integrated over volume. And this quantity here, written without the minus sign, must be some other way that energy can get out of my system. So let's focus then on this other way that energy could possibly escape. Because otherwise, we've now completely accounted for and shown that energy is absolutely conserved in our system as long as we can understand this alternate route for energy to get out of our system. So let's take a look then. Try to rewrite this a little bit. P out. What is the other way? And if we look at the form that we have this integral, excuse me here, I've got this integral over the volume of my experiment. I've got 1 over mu naught. And now here is something interesting. What I have in here is two derivatives, right? I've got a product of two terms, and I've got a sum of two terms, and each term has like the derivative of one field times the other field, or the derivative of the other field times the derivative of the one. This looks like some kind of derivative of a product. And it turns out there is in fact a famous vector identity that says whenever I have this combination, that is exactly equal to the it's exactly equal actually to the divergence of the cross product of the electric field with the magnetic field. Or in fact, it could be any two different vectors, E and B. This is a mathematical identity that just happens to be always true. So this conversion here is a math identity. It's a vector calculus identity. And that's something that you can prove for yourselves. And may be part of the exercises, actually. Now, here's the final manipulation that we can make. And then we can close this discussion. The final manipulation is, notice I have an integral, right, of a divergence. Now, as you know, the integral of a derivative gives you your function back again. But I have a triple integral. So basically, one integral gets used up undoing this derivative. And what I'm left with then is a double integral. And double integrals, as you know, are surface integrals. So what we really have here is an example of the divergence theorem again. We're going to have this is going to equal a surface integral of my quantity without the divergence. The surface integral, of course, then is going to be over the surface of my volume. So this whole volume where this experiment has been going on, right, it has some kind of a surface. So somehow there's energy leaking out of my surface. So there's this P out other that is occurring somehow around my surface via some kind of mysterious process, but at least somehow I can quantify that process. And the surface, I can get that by doing a surface integral. So what's left is dA. And now I've undone one derivative, so what I'm integrating is E cross B over mu naught. Don't forget my constant factor of mu naught. That E cross B, of course, is a vector. And my answer here, power, is a scalar. So what the divergence theorem says is to get this back to being a scalar, it's integrated dot dA. And another way this is often written is just to say that, well, it's an integral, this power that can come out is an integral over the surface of the system of some vector, S, is what the vector is usually called, dot dA. And this S has a famous name, S, which is defined as E cross B over mu naught. It's what you integrate over the surface to get the power that's leaving your surface. This thing has a funny name. It's called the Poynting vector, spelled with a Y. It points in the direction of the flow of energy. I used to think it was like P-O-I-N-T because it pointed, but actually Poynting is someone's name. So this is the Poynting vector, and it gives the power per unit area. Power out per area. And now that we know that there's some way this electromagnetic energy can leave a system, and we can actually calculate the amount by carrying out an integral like this. So I guess the other equation that goes with this is P out through the surface via this other process. That's another box. We now know how to compute the total conservation of energy in the electromagnetic field. And our next discussion will be the form in which electromagnetic energy can mysteriously vanish from our system according to these equations.